Okay. I'm just so excited, you know, I'm ready to get going. Okay. I am Will Melville, and I'm presenting a game theoretical approach to optimal pitch sequencing. So pitch sequencing is the strategic process by which a pitcher chooses the pitch type they want to throw and where they want to throw it. And existing pitch sequencing strategies tend to be based on simple heuristics, like you throw your changeup to set up your fastball, you throw your slider late in the count as a strikeout pitch, you throw your fastball inside, then your slider away. And so we wanted a more technical, robust, analytical solution. And there were three main challenges we wanted to address. First, we wanted our solution to consider the entire sequence of pitches. A lot of existing solutions just consider 2 pitch sequences, so we wanted to make sure we had the full sequence in the at-bat. Second, we wanted to incorporate a pitcher's command skill. Obviously, your ability to hit your intended target as a pitcher, that's going to affect where we recommend you aim your pitch. And then finally, batters, they don't just show up on game day and step in the box. They watch film, they prep, they have their own strategies to try to beat the pitcher. And so we wanted our pitch sequencing strategy to consider what the batter might be doing to try to beat the pitcher. And that idea of opposing strategies lends itself to a game theory model. So we decided to model the batter-pitcher matchup as a zero-sum game, which simply means that if the batter wins, the pitcher loses. If the pitcher wins, the batter loses. And the payoff in our game is runs. So naturally, the batter wants to maximize runs, so the batter is the maximizing player. And the pitcher wants to minimize runs, so the pitcher is the minimizing player. And then the last assumption in our game model is that whatever pitch the batter sees, he's going to respond optimally to that pitch. Or in other words, he's going to use a best response strategy to that pitch. Now that we have this set up, we can start to think about how the pitcher should strategize. So given that the batter is going to respond optimally, naturally the pitcher should choose the pitch that's going to minimize the payoff when the batter responds optimally. So yeah, the pitcher chooses a pitch to minimize the best response strategy. Once we identify that pitch or that pitching strategy, that strategy along with the batter's best response strategy, together they define what's known as an equilibrium in game theory. And one of the interesting properties of equilibria is that sometimes it requires that you randomize. So why would we need to randomize? Hopefully this diagram will make that point. So a batter, it takes some fraction of a second to swing the bat. And because of that, there's a certain point along the trajectory of a pitch where the batter has to decide to swing by that point if they're going to have time to actually hit the ball. So in this diagram, you can think of D as that decision point. So the batter, he can observe the full trajectory of the pitch up to that point. So that's the observable part, PO, observable part of the pitch. He can't observe anything after that point in making his swing decision. So that would be the unobservable part, PU. So as a pitcher, I could throw maybe a fastball and a curveball, and I could throw them along a similar initial trajectory, so a similar initial PO, but the fastball is going to end up in one place, and the curveball is going to end up in another place. And the batter might not be able to tell because they're along the same observable trajectory. So from the pitcher's perspective, it would be unwise to always throw the fastball because it's making it easy for the batter. It's always ending up in the same spot, so he knows where to swing, how to swing. So you want to randomly mix in that curveball sometimes to take advantage of the fact that the batter can't observe the full trajectory, so he has some uncertainty about where it's ending up. So that's why you randomize. And that leads us to our definition of equilibria. So the pitcher is going to choose an observable part of the pitch, and he's going to choose a distribution over the unobservable part of the pitch, which will allow him to randomize. And he's choosing that to minimize utility under the assumption that the batter is choosing his swinging strategy to maximize utility. So that's that top formula on this slide. And then from the batter's perspective, he's choosing his swinging strategy, which he's also allowed to randomize, so it's also a distribution. And he's choosing it to maximize utility under the assumption that the pitcher is choosing a strategy that minimizes utility. And one important thing to note is there is an asymmetry in these two formulas. In the top one, we have the utility with PO as an input. In the bottom, we have PO star as an input. And that's just to point out that the batter gets to actually observe the observable properties of the pitch when strategizing, whereas the pitcher is making that decision when they're deciding on their equilibrium strategy. And defining the utility function was actually what we spent the most time on in our project. And it's where we addressed two of the three challenges I mentioned earlier. So first of all, the utility function is based on expected runs, or really the expected change in expected runs. And we wanted to consider the full sequence of pitches. So we created a new neural network model called Optimus Pitch. That takes as input the batter, the current pitch, and all of the prior pitches in the sequence. And it predicts a distribution of pitch outcomes, which we then use to calculate expected runs. And then we also wanted to incorporate pitcher command into our utility function. So we had a novel pitcher command skill estimation method. Essentially, we assume the pitcher, we're estimating a normal distribution of their execution error. So the center of those normal distributions is their intended target, and then the better command they have, the less variance those normal distributions have. So this is an example with Jacob deGrom. His fastball is the blue curve, his slider is the orange curve. And so our methods estimated that he has better command on his fastball than the slider. Okay, enough of the math. Let's get to some baseball. We're gonna actually do some sequencing now. And we're gonna use this pitch as our motivation. This was the 2020 World Series, Game 4, bottom of the ninth, 2 outs, 2 strikes. Kenley Jansen pitching to Brett Phillips. Single to right center, bad fielding. More bad fielding. Bad base running too. It didn't show in this clip, but Randy Rosarena actually tripped. So he got lucky that the catcher dropped the ball. But most notably, Kenley Jansen looks pretty sad there at the end. So we're going to try to help him out. Even though I was rooting for the Rays in this game, I'm going to help Jansen out now. I'm a nice guy. So, yeah, one last thing before we help Jansen out. One thing to note is that the equilibrium that we solve for depends on what we assume to be observable to the batter. So that line on the bottom, that's sort of the spectrum of observability. All the way on the right, we are assuming the batter is observing nothing about the pitch, and that results in a Nash equilibrium. The other extreme is when we assume the batter can observe the full trajectory of the pitch, and that results in the Stackelberg equilibrium. And then the decision point equilibrium in the middle, that's what I was describing earlier. We're assuming the batter can observe up to a decision point, and then after that, he's uncertain about what the pitch is doing. That was our attempt to give the batter the most realistic set of information. In our paper, we talk about the Nash equilibrium. I don't have it in the slides because the assumption that the batter observes nothing is a bad one, and it results in some weird sequencing strategies, so we left it out. But yeah, let's jump into the Stackelberg. So, as you may remember, the reason why you randomize is because the batter isn't observing the full pitch, and so you're taking advantage of what he's uncertain about. In the case of Stackelberg, though, we're assuming he's observing the full pitch, so there's no real need for the pitcher to randomize his strategy. So in the case of Stackelberg, the sequencing strategy is actually a single pitch rather than a distribution over pitches. And it's a cutter. In the case of Phillips and Jansen, it's a cutter aimed at that blue X. So the box is the strike zone for reference. And then that gives an expected utility of 0.007. And the pitch that Jansen actually threw is that black X, which had a utility of 0.037. So remember, Jansen's trying to minimize utility, so the Stackelberg equilibrium looks like a much better strategy than the pitch he actually threw. The red X, if you're curious, that's if you ignore the execution skill, so you're assuming Jansen is hitting his intended target with certainty. That's the best pitch he can throw, and that gave a utility of negative 0.07. Okay, next up is decision point. So we do have some unobservable properties now, so now the sequencing equilibrium is a distribution over pitches rather than just an individual pitch. So the plot on the right, that is the location of the pitch at the decision point, which we set at 24 feet from home plate. The color gives the usage rate of that pitch and the equilibrium strategy, and the shape of the point gives the pitch type. And then the plot on the left, if you just sort of project those pitches forward to home plate, they end up at the plot on the left. So decision point utility was negative 0.02, which better than the actual pitch that Jansen threw, which you remember was 0.037. So once again, it looks like this strategy is an improvement over the strategy that Jansen actually used. One of the interesting things we found with this equilibrium in particular, if you notice on the left, the pitch that Jansen is supposed to throw with highest likelihood is a slider below the zone. So that's that red circle below the strike zone. And the interesting thing we found is that Brett Phillips' optimal best response to that pitch is to swing 100% of the time, which is really surprising, and it seems wrong. And I remember when I told my dad this, he said, I think he did the math wrong, which was annoying, but it also motivated me to investigate why that was the case. And if you look at the plot on the right, you can see that that slider and those two sinkers in the bottom half of the zone, they're sort of near each other in the decision point. And especially when you factor in Jansen's execution score, all three of those pitches are going to be passing through a similar set of decision points. And so what that means is, from Phillips' perspective, he can't really tell those pitches apart under the assumptions of this game. And what we found is that the cost of taking those sinkers in the bottom half of the zone is much higher to Phillips than the cost of swinging at the slider. So because he can't tell them apart, and because the cost of taking the sinkers is so much worse than swinging at the slider, it ends up being best for him to just swing and basically just hope it's not the slider. So yeah, we thought that was really interesting. There's the big buzzword in pitching on pitching Twitter of tunneling, and I think potentially the decision point equilibrium can provide some tunneling strategies. Like for example, here I would recommend to Jansen, you should try to tunnel your slider and your sinker, and that'll confuse hitters. So to wrap things up, you can think about these equilibria as upper bounds on the pitcher's utility. And the reason why they're upper bounds is because we're assuming the batter is going to respond optimally. But as we all know, batters don't always respond optimally. Sometimes they make bad swing decisions. But if they do make a bad swing decision, the expected utility isn't going to go up. It's obviously going to get worse. So that's why it's an upper bound for the pitcher. One thing we noticed, the more information that you assume the batter has, the higher that upper bound gets. So decision point in our example had a utility of negative 0.02. The Stackelberg, where the batter has more information, that had an expected utility of 0.007, so the upper bound went up. But yeah, so our conclusion was, if you can find an equilibrium strategy, whether it's Stackelberg or decision point, that's negative, as a pitcher, that means you know that on average, if you use that strategy, even if the batter does everything right, you're still winning that pitch. And in the cases where the batter does something wrong, you're doing even better than what the equilibrium suggests. So our conclusion was that both the Stackelberg and the decision point equilibrium would make viable pitch sequencing strategies. And that's everything. Thank you.
I was a little, most of your presentation I understood perfectly, which is rare in these things. But I was a little confused about the randomization aspect. So if I understood correctly what you're saying, is it accurate that what you were saying is that the randomization is huge for the batter? A huge variable in the success of the batter is his ability to adjust to the randomization after the fact, whereas the pitcher, it would appear to be more his skill before the fact. Is that accurate? And not quite getting to what I was trying to ask. It's got to be the big difference between hitters is there their decision point. If a hitter has you said it was 18 feet before the plate or something, but for some hitters it's got to be 16, and some it's got to be 22, and that's got to be a big difference among hitters. So how did you deal with that issue in the study? Or to put it another way, is it any hitter who can't decide between those two pitches accurately, or is it just Brett Phillips?
Yeah, so that's a really good question. Decision point is fixed at 24 feet for all hitters, and that's just because I'm not a cognitive scientist, and that's kind of the best I could come up with. But these recommendations are specific to Brett Phillips because of the Optimus pitch model. So yeah, so this model, which is sort of the brunt of our utility function, it's batter specific. So we actually have a batter embedding, which is just a vector representation of a batter. So yeah, if it was Kevin Kiermaier instead of Brett Phillips, it would have been a different recommendation.
Right. Well, anybody who's a big baseball fan knows that Brett Phillips probably doesn't make those decisions as well as
right.
So it would. I would get more out of your. I got a lot out of your study, but I'd get more out of it if I had some idea of where we go to figure out how that decision point varies from hitter to hitter. Does that make sense to you?
Yeah. And I don't know.
Yeah.
That's a tough question.
Sure. Well, different people have different skills, and if you make a contribution, that's great. Thank you, sir.
Yep.
Yeah, really interesting, really strong stuff. Took a while to digest all the notation, and just one compliment. I was like, why is this guy wasting his time with this Shackelford thing? And I looked it up, and I'm like, why? Perfect information. And then you just explained it, like, hey, if you can always generate positive value even when the batter has perfect information, then that's a good sequence. Question. Just a very basic question, like how long of a sequence are you looking at a time? Just like a tuple of pitches, one after the other, or a whole sequence of the entire at-bat, or?
Yeah, so the pitch sequence starts when the at-bat starts, so it's just, if it's like an 18 pitch at-bat, it'll be that full prior 17 pitches.
Okay, all right, just making sure. Did you find that in general that the pitchers and batters follow that equilibrium? Do they play the game theory intuitively well?
That's a great question, and it's tough to tell with pitchers because, in the decision point, for example, your usage, you're mixing over pitch strategies. So we're gonna get the video again. So that blue triangle in the bottom right, that's the probability that Jansen throws that pitch in this strategy is really low. But if he did throw that pitch, it went I can't say, oh, he's not behaving under game theory, because technically it's possible he could throw that pitch. It's easier to judge in the Stackelberg equilibrium because it's just one pitch, so we actually did do that. We went through all the data and said, when did the pitcher throw the right pitch type, and how close were they to the right location? And I can't remember the exact numbers, but they didn't always throw the right pitch type, as you can imagine. And then for hitters, we did the same thing. We went through and said, how many times did the hitter make the right swing decision? And for Stackelberg, I think it was in the 70s percentage of the time or something like that. In the decision point, it's interesting. The batter actually can't behave optimally sometimes in the decision point. And we have an example in the paper of that. The batter's allowed to have a mixed strategy too. And so we have an example in the paper where the mixed strategy is to swing 80% of the time if he observes that decision point, which from a practical perspective means I'm batting, I see the pitch, I identify the decision point, which is a couple inches square, which is already impossible. And then I say, okay, I remember I need to swing 80% of the time at that pitch. So then I pull out my 80% weighted coin, flip it, comes up heads, then I swing. So that's why a key thing here is it is an upper bound. Batters aren't going to behave optimally. So.
And probably, and there's error too. They're just they're not flipping a coin. Last question for me is, Oh, did you find that the recommended sequence were generally were the same as the common heuristics that people kind of live by, or were you able to like blow up one of those heuristics, like, oh no, they say do this, but you shouldn't?
So yeah, we didn't quite get to that. We have one of our lab research assistants is working on that right now, but yeah, we haven't gotten there yet, but that's what we're looking into next.
That'd be cool.
Tell your father that the reason he's wrong is that he's asking Brett Phillips to do something that Brett Phillips is not capable of doing.
Right, yes, thank you.
So I think one of my questions was going to be deviation from like rational expectation. Like what are the causes that would make them deviate from your recommendations? And I think you start to allude to that, but can you summarize on both sides what are the deviations? Why would they deviate from your equilibrium behavior?
So yeah, decision point, like I said, it's literally impossible sometimes. For Stackelberg, I think it's just really hard. And also Stackelberg, we're assuming they're observing the full trajectory, which they don't actually get to do. So for them to behave optimally in the Stackelberg, they would need to have like a good internal physics projection model to where...
I guess that goes back to Bill's point that if they could minimize the distance between the decision point and the Stackelberg equilibrium, that's where the advantage will be, right? If somebody becomes better and better at driving those together, you'll get a better hitter, right?
Yep.
Okay, great. And then can you tell us more about the Optimus pitch? You spoke about it briefly, but you're obviously very proud of it, and rightfully so. So can you tell us a little bit, like, what's behind that black box? What's in there in that big blue circle?
Yes, yeah, I am proud of it. I spent like, I became sort of obsessed with it. It was like my white whale, and I couldn't think about anything else for like a whole month, and I tried everything I could think to try. But eventually I didn't use like a standard recurrent neural network. Like I didn't use like LSTM or GRU. I tried some of those, and they didn't work as well as I had hoped. And I have some ideas of why, but basically this is, it's like two different dense networks, so multi-layer perceptrons. And so one of them takes as input a hidden state and the outcome of the pitch, and it calculates a new hidden state. And then, so that's like the top part, and then the second part takes that hidden state that's being calculated and the current pitch and the batter, and then it outputs the probability over outcomes. Yeah, so it doesn't have like I'm not a great neural network deep learning guy, but it doesn't have, LSTM has like a forget gate. It just remembers anything. Yep, exactly. Yep.
Great, super interesting. So on your on the last slide, you showed the difference between the Stackelberg equilibrium and the decision point equilibrium, and you had like a minus. Yeah, exactly. Can you translate those numbers into baseball for me? So, like, if a batter could achieve the Stackelberg equilibrium, does that correspond to like one more hit per? Like, what does that correspond to?
So. Yeah, really good question. It's all based on like run expectancy matrices. So every base runner out state has a run expectancy. Mm-hmm. And so negative just means your new state has less run expectancy than your old state. So like if you throw a strike, it'll be a negative expectancy. And then positive means something good has happened. So it's a ball or you got a hit or something.
Yeah. But is that difference between negative 0.18 and 0.007, is that big? Like if the batter, like Bill was suggesting, if the batter got really good at moving that decision point forward, is that worth the effort to do that? Like I just don't know what those numbers, whether that changes in the outcome.
So it's measured in terms of runs. So it's like clearly that's not big because it's like 0.2 of a run. And then, yeah, like run expectancy, I think it's like an average of half a run per inning. So if you think of it in that context, the 0.02 is like a fifth of what they would score in a normal inning. So
Okay,
Yeah,
but
I don't-
that's noticeable, yeah, okay, yeah, great, all right, thanks. I think my other questions were covered.
Okay, thank you.